Top 30 Quantum Computing Researcher Interview Questions and Answers. Quantum computing is rapidly transforming technology, offering breakthroughs in cryptography, optimization, and simulation of complex systems. For aspiring quantum computing researchers, preparing for interviews requires a solid understanding of quantum mechanics, algorithms, and hardware. This guide presents the top 30 interview questions and answers that cover essential concepts, practical skills, and problem-solving approaches. Reviewing these questions will help candidates confidently demonstrate their expertise and analytical abilities in quantum computing research. 1. What is a qubit? A qubit, or quantum bit, is the fundamental unit of quantum information, analogous to a classical bit, but with unique quantum properties. Unlike a classical bit, which exists as either 0 or 1, a qubit can exist in a superposition of both states simultaneously. This property enables quantum computers to perform parallel computations. Qubits are implemented in various physical systems, including superconducting circuits, trapped ions, and photons, each with distinct advantages and challenges. 2. Explain superposition. Superposition is a core principle of quantum mechanics, allowing a qubit to occupy multiple states at the same time, instead of being limited to a single classical state. This enables quantum computers to evaluate many possibilities simultaneously, drastically increasing computational power for certain problems. Superposition is typically represented mathematically as a linear combination of basis states. Maintaining superposition requires minimizing decoherence and environmental interference to preserve quantum information. 3. What is quantum entanglement? Quantum entanglement is a phenomenon where two or more qubits become linked such that the state of one instantly determines the state of the other, regardless of distance. This correlation enables highly secure communication protocols and forms the basis for many quantum algorithms. Entanglement is essential for tasks like quantum teleportation, superdense coding, and error correction, and it represents one of the fundamental distinctions between classical and quantum information systems. 4. Define quantum gate. A quantum gate is a basic operation that manipulates qubits, similar to classical logic gates, but capable of handling superposition and entanglement. Gates are represented by unitary matrices and can perform rotations or transformations on qubit states. Common gates include Poly-X, Hadamard, and CNOT. Quantum gates are building blocks for quantum circuits, enabling complex computations by applying sequences of operations while preserving coherence and quantum information. 5. Explain decoherence. Decoherence occurs when a quantum system loses its quantum properties due to interaction with the environment, causing superposition states to collapse into classical outcomes. It is one of the main challenges in quantum computing, as it introduces errors and limits computation time. Controlling decoherence requires isolating qubits, using error correction codes, and employing techniques like cryogenic environments. Minimizing decoherence is essential to maintain reliable quantum computations. 6. What is quantum supremacy? Quantum supremacy refers to the milestone where a quantum computer can solve a problem that is practically impossible for classical computers in a reasonable time frame. It demonstrates the computational advantage of quantum algorithms over classical methods. Achieving quantum supremacy does not necessarily mean solving useful problems yet, but validates the feasibility of quantum computation. Experiments like Google's Sycamore processor have demonstrated this concept in controlled tasks. 7. Name quantum algorithms. Quantum algorithms are procedures that run on quantum computers, leveraging superposition, entanglement, and interference to solve problems more efficiently than classical algorithms. Notable examples include Shor's algorithm for factoring large integers, Grover's algorithm for unstructured search, and the quantum approximate optimization algorithm, QOA, for combinatorial problems. Quantum algorithms are applied in cryptography, optimization, machine learning, and simulations of physical systems, offering exponential or quadratic speedups over classical counterparts. 8. Explain Grover's algorithm. Grover's algorithm is a quantum algorithm designed for searching unsorted databases more efficiently than classical methods. While a classical search requires O(n) steps for n items, Grover's algorithm achieves it in roughly O (n) steps using amplitude amplification. It works by initializing qubits in superposition, applying a series of oracle and diffusion operations, and enhancing the probability of the correct solution. Grover's algorithm demonstrates the quadratic speedup achievable in quantum computing. 9. Explain Shor's algorithm. Shor's algorithm is a quantum algorithm that factors large integers efficiently, threatening classical cryptographic systems like RSA. It exploits quantum parallelism and the quantum Fourier transform to find the period of modular exponentiation functions, which then leads to factors. Classical factoring is exponentially slow for large numbers, but Shor's algorithm can solve it in polynomial time. It exemplifies the power of quantum computing in solving problems infeasible for classical machines. 10. Differences between classical and quantum computing. Classical computing uses bits as the basic unit of information, which are either 0 or 1, performing operations sequentially. Quantum computing uses qubits that can exist in superposition, enabling parallel processing. Quantum computers exploit entanglement and interference, allowing them to solve certain problems exponentially faster. While classical systems are highly reliable and mature, quantum computing is still emerging, with challenges like decoherence and error correction limiting large-scale practical implementation. 11. What is quantum teleportation? Quantum teleportation is a process where the state of a qubit is transmitted from one location to another without physically moving the particle. It relies on entanglement and classical communication. The sender performs a joint measurement on the qubit to be teleported and one entangled qubit, sending the result to the receiver. The receiver applies specific quantum gates based on the measurement, recreating the original state exactly at the new location. 12. Explain error correction in quantum systems. Quantum error correction protects quantum information against decoherence and operational errors. Unlike classical error correction, it must preserve superposition and entanglement without directly measuring the qubits. Techniques include using multiple physical qubits to encode a single logical qubit and applying stabilizer codes, such as the Shor code or surface code. Error correction is essential for scalable quantum computing, as it allows long computations to run reliably despite noise and imperfections in hardware. 13. Define quantum annealing. Quantum annealing is a computational method that uses quantum fluctuations to solve optimization problems by finding the global minimum of a function. It involves gradually evolving a quantum system from an initial easy-to-prepare ground state to the problem Hamiltonian, allowing tunneling through energy barriers. Quantum annealing is particularly useful for combinatorial optimization, scheduling, and machine learning. D-wave systems are practical implementations of quantum annealers. 14. What is QOA? The Quantum Approximate Optimization Algorithm, QOA, is a hybrid quantum classical algorithm for solving combinatorial optimization problems. It combines parameterized quantum circuits with classical optimization to approximate solutions. QOA encodes a problem into a Hamiltonian and alternates between applying problem-specific and mixing operators. By tuning parameters iteratively using a classical optimizer, it can achieve near-optimal solutions. QOA is well suited for NISQ devices due to its shallow circuit requirements. 15. Explain quantum Fourier transform. Quantum Fourier transform, QFT, is a linear transformation on qubits analogous to the classical discrete Fourier transform, but exponentially faster. It maps computational basis states into frequency components, enabling efficient period finding. QFT is a key component of Shor's algorithm and other quantum algorithms. Implemented using Hadamard and controlled phase gates, it allows quantum computers to perform operations like phase estimation and signal processing much more efficiently than classical counterparts. 16. Applications of quantum computing. Quantum computing has applications in cryptography, optimization, drug discovery, material science, and machine learning. It can break classical encryption with Shor's algorithm, accelerate search with Grover's algorithm, and simulate quantum systems beyond classical capabilities. Industries like finance, logistics, and pharmaceuticals can benefit from faster computations for risk analysis, scheduling, and molecular modeling. As hardware improves, practical applications are expected to expand, enabling solutions to problems previously infeasible for classical computers. 17. Quantum hardware types. Quantum computers are built using different hardware platforms, each with strengths and weaknesses. Common types include superconducting qubits, trapped ions, topological qubits, photonic systems, and neutral atom qubits. Superconducting qubits offer fast gate speeds. Trapped ions provide long coherence times. Photonic qubits excel in communication. Hardware choice affects scalability, error rates, and algorithm suitability. Researchers often select hardware based on the type of computation and available technology. 18. What is a Bell state? A Bell state is a specific type of maximally entangled two-qubit state with strong correlations. There are 4 Bell states, each representing a different superposition of qubit pairs. Measuring one qubit immediately determines the state of the other. Bell states are fundamental in quantum information protocols like teleportation, superdense coding, and quantum cryptography. They illustrate the non-locality and entanglement properties that make quantum computing unique. 19. Explain measurement in quantum mechanics. Measurement in quantum mechanics collapses a qubit's superposition into one of the basis states, probabilistically determined by amplitudes. Before measurement, the qubit exists in multiple states simultaneously. Measurement irreversibly affects the system, destroying superposition and entanglement of measured qubits. In quantum computing, measurement is a final step to extract computational results. Designing algorithms requires careful management of measurement timing to preserve quantum information until the computation concludes. 20. What are qubit systems? Qubits are quantum systems with d-level states, generalizing qubits, 2-level systems, to higher dimensions. A single qubit can encode more information than a qubit, potentially reducing the number of physical elements required for computation. Qubits are used in high-dimensional quantum communication, error correction, and simulations. They offer advantages like increased information density and robustness, but are more challenging to implement experimentally compared to traditional qubit-based systems. 21. Quantum simulation examples. Quantum simulation uses quantum computers to model complex quantum systems that are infeasible for classical computers. Examples include simulating molecular structures for drug discovery, studying high-temperature superconductors, and modeling chemical reactions. Quantum simulators can provide insights into condensed matter physics and quantum phase transitions. These simulations exploit superposition and entanglement to represent many body systems efficiently, enabling researchers to predict physical properties and optimize materials without expensive or impractical laboratory experiments. 22. Explain topological qubits. Topological qubits are a type of qubit that stores information in the global properties of particles, making them resistant to local noise and decoherence. They rely on exotic quasiparticles like anyons, whose braiding operations encode quantum information. This approach offers fault-tolerant quantum computing with lower error rates compared to conventional qubits. While still experimental, topological qubits promise scalable quantum systems with improved stability, which is critical for long computations and practical applications. 23. What is noisy intermediate-scale quantum? NISQ refers to current quantum devices with tens to hundreds of qubits that are prone to noise and lack full error correction. These machines can perform meaningful computations, such as optimization, simulation, and algorithm testing, but results are limited by decoherence and gate errors. NISQ devices are valuable for developing algorithms, benchmarking hardware, and exploring quantum advantage, representing a transitional stage between small experimental setups and fully fault-tolerant quantum computers. 24. Quantum cryptography basics. Quantum cryptography uses quantum mechanics to secure communication. The most notable application is quantum key distribution, QKD, where two parties can share encryption keys with security guaranteed by quantum principles. Any eavesdropping introduces detectable disturbances due to the no-cloning theorem and measurement collapse. Quantum cryptography promises unbreakable encryption compared to classical methods and is used in secure communication, banking, and governmental data protection, laying the foundation for next-generation cybersecurity. 25. Quantum machine learning overview. Quantum machine learning combines quantum computing with classical machine learning to enhance speed and efficiency for certain tasks. Quantum algorithms can accelerate data processing, pattern recognition, and optimization in high-dimensional spaces. Techniques include quantum classifiers, variational circuits, and quantum neural networks. While still experimental, quantum machine learning has potential in finance, drug discovery, and image analysis, offering computational advantages that exploit superposition and entanglement to handle large datasets more efficiently than classical methods. 26. Challenges in scaling qubits. Scaling qubits faces challenges like maintaining coherence, minimizing errors, and implementing reliable control over many qubits. Physical limitations, noise, and interactions with the environment complicate large-scale architectures. Connectivity and crosstalk between qubits must be managed carefully. Additionally, error correction and fault-tolerant designs require many physical qubits per logical qubit, increasing complexity. Overcoming these challenges is essential for practical, large-scale quantum computing capable of solving real-world problems efficiently. 27. Explain hybrid quantum classical systems. Hybrid quantum classical systems combine quantum processors with classical computers to optimize performance. Classical computers handle data input, error correction, and optimization parameters, while quantum processors perform specialized tasks like simulation or optimization. Algorithms like variational quantum eigensolver (VQE) and QA use this approach, leveraging the strengths of both systems. Hybrid architectures are particularly useful for NISQ devices, enabling practical problem-solving despite limitations in qubit number and coherence times. 28. What is quantum error mitigation? Quantum error mitigation reduces the impact of errors in quantum computations while fully implementing error correction. Techniques include extrapolation to zero noise, probabilistic error cancellation, and post-processing measurement results. These methods improve computation accuracy on NISQ devices, where full fault-tolerant error correction is impractical. Error mitigation allows researchers to extract reliable results from noisy quantum systems, making near-term quantum algorithms more effective for optimization, simulation, and machine learning applications. 29. Key research tools. Quantum computing researchers use hardware platforms, superconducting qubits, trapped ions, software frameworks, Qiskit, Cirq, PennyLane, and simulators for algorithm development. Tools include quantum programming languages, visualization tools, and benchmarking software to analyze gate fidelity and coherence. Researchers also employ error correction codes, tomography methods, and cloud-accessible quantum devices for experimentation. These tools facilitate designing, testing, and validating quantum algorithms while exploring hardware capabilities and limitations. 30. Future of quantum computing research. Quantum computing research aims to develop fault-tolerant, scalable quantum systems, discover new algorithms, and expand applications across cryptography, optimization, and material science. Progress includes improving qubit coherence, error correction, and hybrid quantum classical techniques. Researchers are exploring high-dimensional qubits, topological qubits, and photonic platforms. As hardware matures and algorithms evolve, quantum computing has a potential to revolutionize industries, solve previously intractable problems, and provide a foundation for next-generation computational technologies. Mastering these 30 quantum computing interview questions equips candidates to articulate both theoretical knowledge and practical applications. As quantum technologies evolve, demonstrating expertise in algorithms, hardware, and emerging research trends will set you apart in interviews. Continuous learning and hands-on experimentation are crucial to staying competitive in this fast-paced field. Use this guide to refine your preparation and confidently showcase your capabilities as a quantum computing researcher.